Hi, John Valvano here. Today we're going to talk about the fundamentals of PCB construction layout. And shown here on this are some of the various forms in which our printed circuit board will look like as it's being developed. In this shot, it shows what it looks like in the design tool called PCB Artist. And then in Lab 6, you're going to create a version of your board, which is actually made out of paper. It's a cardboard with the front side and the back side taped onto it. And so the first step will be to design the SCH and then lay out the PCB, print this file right here onto paper, and then put that paper into a box. Okay? And that's all we're going to do for Lab 6. So when we get on to 7, 8, and 11, we'll go further and take that printed circuit board and actually produce it. We'll actually produce the printed circuit board, put it inside of a real box, power it up with a real battery, and we'll have our system. Okay. But for today, I'd like to talk about the fundamentals of the PCB construction. This is shown here in Chapter 9, and there's a YouTube video of me starting Lab 6. All right. If you cut into the printed circuit board, you will see that it has layers. We're going to have a top copper layer and a bottom copper layer separated by a substrate which is insulated. Okay? And so we're going to see that a cross section, there's a copper layer on the top and a copper layer on the bottom. Okay? And what's going to happen is we are going to remove some of the copper in order to construct or to build our circuit. Okay? Here are some of the obvious consequences of Ohm's law. Right? And so if you think about the trace in your circuit, if you think about that trace will have a certain resistance. And that resistance is going to be a function of the width of that trace and the length of that trace. Right? And according to the equation, the resistance of this trace is going to be the resistivity of copper times the length over the area. Okay? And since the thickness of the copper is a constant, what you can control are the width and the length. As the amount of current goes up, the power applied to that trace will go up, and the consequence will be thermal heating. Okay? The bottom line is, the more current that you want to deliver, the thicker that trace has to be in order for it to not overheat. We're not going to use a lot of current in our class, and so the bottom line to our designs is we're going to have thick traces and thin traces. Okay? So in particular, a thin trace might be 8 milli-inches, and a thick trace will be about 20 milli-inches. And so for the digital signals, we're going to use an 8 mil, and for the power, the plus 3.3, the ground, we're going to use a bigger or 20 mil. Okay. There are some specifications from the manufacturer, from Advanced Circuits, with whom we're going to have the boards made. And we saw last time that I suggested 8 mil for the trace. It actually could be 6 mil. But when you're on the edge of things, sometimes it doesn't work. So we're going to have a trace width, suggested trace width of 8 mils. Okay? And then there's this issue of clearance. Clearance is defined to be the difference between two objects. And so this yellow circle represents the copper on both sides of a via, and the red represents the copper on the top side, and the blue or cyan represents the copper on the bottom side. And so there is a minimum trace. There is a minimum trace clearance between this piece of copper and that piece of copper, and that has to be 6 mils. The smallest hole we can drill is 15 milli-inches, and so this is an example of the smallest via that I can create. A via goes from the top to the bottom, okay? And this hole is 15 mils, and the pad itself is 25 mils. Okay? And so when we use the program, you're going to see the red is the top copper. This red here is going to be the pad onto which the processor is soldered. And then the yellow, like I said, shows you a via where that yellow actually exists on both the top and the bottom. And the hole is plated through. In other words, copper is on the inside of this hole as well. Cyan is the bottom copper. No orange is shown here, but if you were in the program, you're going to see orange. That's called a mask. Mask means don't solder here, and the mask will make it very easy for you to solder. And so there'll be mask on the top and the bottom. Okay. So again, make sure you don't change the design specifications. These are built into the program. It'll give you an error if you violate any of these specifications. All right, some of the design you can change and some of it you can't change. So in this picture, it shows all the things that we put in the starter file. You shouldn't change them. The first is how we're going to debug the processor. In other words, your processor on your labs 6, 7, 8, and 11 is going to use a JTAG debugger. Of course, lab 6 is just a piece of paper. Nevertheless, we're going to leave this on there. And these four signals here, tied into PC3, 2, 1, and 0, will be our debugger. And those 5 wires with ground are going to connect over to your launch pad. Your launch pad will actually be the debugger for this target processor. So we'll have some sort of 5-pin cable going tethered between the prototyping system and your launch pad. Okay. Then there's a bunch of power signals. As you can see from this diagram, there's actually 2 powers. One of them is 3.3, and 3.3 is tied to a lot of different places. All of these places here are 3.3, so hook them up. This one's actually the analog, which is also 3.3, and the others are all digital. And then there's one more power line called VCCC, you see right here. It's not actually connected to anything externally, but internally it's a low voltage supply for the processor itself. So we're going to add these 4 bypass capacitors to the various VCCC, VDDC signals in order to make it work. Again, these are connected up and suggested by the processor. Don't change it. Okay, so again, there's actually 2 digital voltages. The one that you are supplying into the chip, which is 3.3, and there's actually a 2.5 volt output of the processor. Other than these 4 caps, don't connect anything to it. Here's the reset. It's fairly obvious. You push this reset button, the reset signal goes low, and your processor is reset. You let go of the button, this goes to 3.3, and the processor runs. Okay. The last is probably the hardest thing for us to get working, and that's the crystal. Okay. This thing runs, as you might imagine, on an external crystal. Here it is right there. And together with the crystal and these 2 caps, these signals here are going to oscillate at 16 megahertz with a very, very accurate frequency. But again, we're going to lay this part out for you. Don't move it around. Okay? Here's a zoomed in of my solution to lab 6 and 7. What you're going to see here is this one here is the crystal. All right, that's Y1, and it is very close to the pins. And then here are the 2 caps, the two 10 picofarad caps. And there's a couple of things I want you to do, and that is I want you to not modify the shape and location of the crystal. We're going to wire it up in this way. These 2 pins are going to be ground, and then it's going to work. Okay. The other thing I don't want you to change is look at the location of the external capacitors. See, there's C3, C9, C11, C6, C5, C8, C12. You see something else, and there's then C7. These are the capacitors that will make the processor work. Okay? And so my suggestion is you leave these capacitors in their positions and don't move them. You will wire them up, of course. Okay? Here's where I put the JTAG connector. Again, it doesn't really matter where you put it as long as you hook it up to port C. All right. There's a couple of ways to route signals, and this is particularly interesting for shared signals like the ground. And so the simple way to connect ground is to tie this one to ground and tie this one to that one and tie this one to this one, and then they all get ground. Unfortunately, this wire right here has a finite amount of resistance. So it turns out that the current in this device is going to affect the voltage of this ground signal. Okay? And so in that way, there is a coupling of the behavior of module 2 to the behavior of module 3. Now, this is not a bad problem in this class because these currents are very low, and that 20 mil trace that we're going to have can solve this problem. So again, this is a problem when the currents are high or when the frequencies are high. Okay? And we have neither of that in this class. If you did have high current or high frequency, the way to do it is to have a single point in ground and then separately connect all the modules to that one pos so that the current in this module does not affect the voltage at the ground pins of these other two. Okay? Again, something else for you not to change. We're going to have a battery that comes in. This was going to be somewhere between 3.7 to say 4.8 volts. That's going to come off a battery. And then we're going to use something called a regulator, which is going to take the battery and produce for us a nice clean 3.3 volt power line. These two caps we're going to put on here to stabilize this regulator. We're going to talk more about regulators next week, but suffice it to say that we're going to have a regulator on there, and in Lab 6 you're going to choose either this LP2950 if your current is less than 100 milliamps, and if your current is between 100 and 500 milliamps, you're going to switch the part over to this one. Okay, it'll fit into the same socket, so it'll have the same circuit. We're just going to change the chip number. Okay? This is obviously a power light that lets you know that power is applied. All right, so again, this is in the starter file here. Leave it or change it out to this if you want to have more current. All right, there's a lot of fundamental theories going on in the next couple of slides. The first is all the chips are going to have caps, bypass caps like you had in 319K. Remember in 319K we gave you a 7406, and then we gave you a cap to tie to between pin 14 and ground. Okay? We gave you a 0.1 microfarad cap to bypass the power line. So all of our chips are going to have a cap on the power line, and that cap is going to be as close to the chip as possible. Okay? Now the next two we're not going to do, but they're good design practices. Good design practice is going to create a ground plane, and that ground plane is going to shield. You can see the ground plane on my solution here. This whole bottom side is actually a ground plane, but you're not going to do that for the following two reasons. It's really hard to debug because ground is like everywhere, and more importantly, you're going to make a mistake, I promise. And changing or fixing it is going to be very hard with a ground plane. Okay. Another good design rule that we're not going to need you to do here in 445L is separating the digital circuits from the analog circuits. In order to have very high fidelity analog circuit design, generally we're going to have two grounds, one for the analog system and one for the digital system. But in this class, we're going to mix all the grounds together and not worry about this on your first PCB. All right. So again, what you're going to see in here is all your chips are going to have bypass capacitors. Okay, and that's going to be 0.1 microfarad caps, and we're going to put them next to that chip. All right, here's some design rules, and we're going to show you some examples of it, but let's go ahead and list them. Actually, the hardest thing, the most fun thing, just like writing the header file for a software system, the most fun thing about a PCB layout is the placement of the parts. And so this is where you want to spend most of your time. You want to think about the different places to put the parts. Should I put it on the left? Should I put it on the right? Should I put these two together? Where are my connectors going to go? How am I going to fit it all into the box? Okay, because the placement of parts is going to affect how big your board is. And you might need a great big box in order to get everything in there, and that makes it look ugly. Okay, so you got to think about where the connectors are. You got to think of how it's going to be. And if, for instance, just like putting the bypass caps next to the chip, things that go together fit together. That'll reduce the amount of traces you have to get. So again, look at where you place it. It's the fun part. Try this over and over again because there's a lot of difference that can happen. Okay, there's a thing called design rule check, and that makes sure you haven't violated any rules. Do it frequently. That'll let you know you've made a mistake and you've got to fix it before you go on. I use a snap to grid so that things fit together nicely, so that when I'm taking a wire and another wire, they actually connect. But just experiment with what you like. The top silk is a layer that you can put on there to make it look pretty. Put your name and the date and all sorts of debugging information. Now, one of the things I do is I place all of my parts, all of my soldered on parts on the top side. And if you do that, then all of your soldering can be on the bottom side. Now, there are some exceptions to my rule. You can see that I place the buttons and the display on the bottom side, and that allowed me to fit it nicely into the box. And so this rule of placing all the through-hole components on the top side is a suggestion. Okay? Aligning all the chips in the same direction will make it easy to make it less likely for you to solder the chips in upside down. Although I'll violate this rule just to make it simple. Again, a suggestion. Think about how you're going to solder it. Okay, again, if your soldering iron is near something that's got plastic, it's going to melt. And so I try to think about where I'm going to solder and solder on the bottom side rather than have to solder on the top side. Okay, the top and bottom silk can help you debug, can help you build, can help you think. And so make sure you use a copious amounts of silk, labeling this and that. Okay. Design for test. Think about testing. Look at all my test points. Test points can be a couple of ways. Test points can be little bumps. Test points can be two holes close to each other with a U wire soldered onto it. Have at least two ground test points because you're always connecting things up to ground. Okay. All the components are going to have labels. Okay, that way you can see on both sides. I'm going to have a picture on the next one, but we're going to have 45 degree, it's called a miter turn, and I'll show that to you in the next slide. One of the ways to get it to all fit together is if in general you go left to right on one side of the board and you go top down or up and down on the other side, and that way you can pretty much always fit or connect any one thing to any other one thing. Think about ground. Okay, think about how you're going to do ground and do that first because that's going to help you make it all work, and then do the power, and then do the other signals. Okay, this is what I meant about a mitered turn, a 45 degree turn. And so rather than having a 90 degree turn or worse yet, 100. A very acute angle. We are going to change all of our angles to look like this, and for the following two reasons. At high frequency, this is actually a quarter inductor, and this is an inductor. So at high frequencies, this doesn't work. But for low frequencies, what we're going to do is right here at the corner is a place for acid to trap while the board is being made. And it might actually cause a defect. And so in order to help out or increase the yield of our PCB, we're going to have nice wide-angled turns. It also makes the length shorter, because if you think about it, the resistance between here to here is lower than the resistance between there to there, okay? Causing it to run better with a lower resistance. And the other thing is when you show it to everybody, it's going to look awesome. All right. Texas Instruments encourages you to ground a pin that you're not used, but it's also acceptable to leave it not connected. And what I suggest you do is for some, 2, 3, 4, not all of them, but for some of your I/O pins that you didn't use, what I want you to do is route them out and put them on a via, or route them out and put them on a logic analyzer pin. Because then you can use it for debugging, you can use it for fixing, you can use it for changing. And so this shows a cutaway of what I did is I took all of I didn't use port D, so I took port D and I just hooked it up to the logic analyzer. This allows me to use these pins to fix a mistake that I didn't think about while I designed it. Okay, so again, take some 2, 3, 4 of your pins and connect them, route them out to the processor to a via, okay? Or continue routing it to the logic analyzer. Either way, this allows you to stick a wire in here and solder it to someplace where you need to fix something. All right, now we're going to put it in a box. You've got a couple options here in Lab 6. You can use this box, or you could use one of the Maker Studio boxes shown on the website right here, one of these 3 boxes. The starter file will automatically go into this Maker Studio box, into any one of these 3 boxes. This one is the Lab 9 box. This one is like Wood Box 2, and there's the other Wood box. Okay, so the starter file for Lab 6 and 7 will automatically go into this box. You can see this box has some holes already drilled in it. The other possibility is to put it into this Hammond 1593 box. If you want to use this plastic box, you're gonna eventually have to buy it. But in Lab 6, if you want to do it, you're going to have to place this part. There's a part in the library called Hammond 1593, and it'll show you where all the drill holes are for that box. All right, so like I said, the output of Lab 6 is actually just a piece of paper, and that piece of paper is going to fit into a box. Okay, that's the output of Lab 6, and then once we get to Lab 11, we're going to actually build it up and solder it all together for Lab 7. Okay, so in summary, remember, put a lot of test points, connect up the logic analyzer so you can debug it. There's a regulator. All I want you to do is to choose whether to use the LP2950 or the LM2937, okay, depending on how much current you have. Part placement is the funnest part, and also the one that makes the most difference about getting it to work. The routing is the easy part, because then it's just connecting every part to where it's supposed to be. You will create a mock-up, which is a piece of paper. Okay, you're gonna create a piece of paper, and then you will also develop a bill of materials of that system. So Lab 6 is sort of a practice one, and when we get to Lab 7, you're gonna design your own system.